So in this video we will briefly talk about regression and correlation for statistical use. So basically for regression and correlation, the characteristics are it's bivariate data. What is bivariate data means? Bivariate data consists of at least ordered numeric pairs. It could be it will be easily translated into Cartesian diagrams which are consist of x and y axis, and of course both both values are numerics. And here the numerical data are paired by common characteristics. So we have independent values and also dependent values. So mostly it will be displayed as a graph or scatter plot. So here the example of bivariate data. So let's say we have a comparison between a square footage of housing data in x-axis, and on y-axis it has the price. We can see here we have two kind of scatter plot data. First is the large data, and the pink one is the smaller area. In small area we have various price over square footage of housing. So first we talk about regression analysis. So regression is a set of techniques for estimating relationships, and we will focus on them for this chapter. So in this chapter we will focus on finding one of the simplest type of relationships, which is linear. We will see later on you will find a lot of regression analysis, but the most popular one is linear because it's the simplest form of regression analysis. So here regression analysis usually used to determine the regression equation. It's used to predict, as I mentioned earlier, it's used to predict the value of the dependent variable, usually in y-axis, based on the independent variable. So let's say we have price a square footage area of housing compared to price. Usually even if we have a scatter plot, we can say the larger the square footage, the price will be higher. That's the simplest use of regression analysis. And the procedure is quite simple because we just simply select a sample from the population and list the paired data for each observation, and we have to draw a scatter diagram to give a visual portrayal of these relationships, and then determine the regression equations. Despite its simplicity, linear regression is an incredible and powerful tool for analyzing data. But just because fitting a line is an easy task, it doesn't mean that it always makes sense. We will find that with this simple linear regression, there are there are more than just two variables of interest, which is weight and height or force, and also the distance it stretched between the data. Here we have a simple linear regression. In this example, we are trying to fit a line, which is y line, and this y value is equal to beta 0 plus beta 1 multiplied by x to our data. Here x is called the independent variable or the predictor variable, and y is called the dependent variable, or we may say it's a response variable. Before we talk detail about how to fit the data, let's take a closer look at the important quantities from the fit. This beta 1 is the slope of the line. This is one of the most important quantities in any linear regression analysis. A value very close to 0 indicates little or to no relationship. Larger positive or negative values indicates larger positive or negative relationships, respectively. For example, here we we can relate the force for stretching a spring and also the distance that the spring stretches. In this example, we can simply say that the slope from the linear model here is the spring constant for our spring. Beta 0 is the intercept of the line. So in order to actually fit a line, we will start with a way to quantify how good a line is. We will then use this to fit the best line we can. One way to quantify a line's goodness is to propose a probabilistic model that generates data from lines. Then the best line is the one for which data generated from the line is most likely. This is commonly used technique in statistics, proposing a probabilistic model and using the probability of data to evaluate how good a particular model is. We do a simple linear regression. First, we need a probabilistic model for linearly related data. First, we have to select data, find the statistics that will estimate the three population parameters, which are slope parameters, y-intercept parameter, and also standard deviation. Here we observe data points, which is x1, y1, x2, y2, etc. until xn, yn, where we assume that as a function of xi, each yi is generated by using some true underlying line, which is y equal to beta 0 plus beta 1x, that we evaluate at xi and then adding some Gaussian noise. Here we need to remember that we will have noises. This noise represent the fact that our data won't fit the model perfectly. We will model the noise, Gaussian noise, as an error, and the noise variance are all treated as fixed but unknown quantities. So, assuming that this is actually how the data we observe are generated, then it turns out that we can find the line for which the probability of the data is highest by solving with optimization. Where minimum here, this optimization known as the least square linear regression problem. So we can solve this regression analysis by using least square principle to obtain beta 1 and beta 0. For noting that in order to finish this regression analysis, we need to make several assumptions which is underlying this linear regression. First, for each value of x, there is a group of y values. So it's not only one y value. So, and these y values are normally distributed. And also the means of this normal distribution of y values are lie on the straight line of regression. The standard deviation of this normal distribution are also equals. Then the y values are statistically independent, which means that in this selection of sample, the y values chosen for a particular x values do not depend on the y values for any other x values. Let's take a look at this example. Here on x-axis we have average annual rainfall, and in y-axis we have average sale of sunglasses divided by 1,000. So what we need to do? First, we need to make a scatter plot. We need to make a scatter plot here where y-axis is the average sale of sunglasses and the x-axis is average annual rainfall. Here we see some relationship, but later by the end of this course we will also discuss what kind of relationship here, because it will be more detailed. It could be just correlation, and this correlation sometimes is causation and sometimes it's not. After we make a scatter plot, we need to find the least square line. Using this table, it will be easily to get a least square line. And then we need to standardize the error of estimate. This standard error of estimate measure the scatter or dispersion of the observed values around the line of regression, and we have this formula to estimate the standard error. So here we have the standard error values, and then we need to test whether our values is correct or just simply the values is valid or not. First, we can use F distribution. This F distribution, each member of this family of F distribution is determined by two parameters: the numerator degrees of freedom and the denominator degrees of freedom. And this F values, F distribution cannot be negative, and it is a continuous distribution. The F distribution is positively skewed, and the values range from 0 to unlimited, but still positive. And we need to make hypothesis regarding this simple linear regression that we made. How do we make a hypothesis? First, don't forget we need to make the null hypothesis and alternate hypothesis. Here, for null hypothesis, x and y are uncorrelated. For alternate hypothesis, the x and y are correlated. So for null hypothesis, we can say beta 1 equals to 0, and beta for alternate, beta 1 is not equal to 0, and this can be tested using ANOVA. If you still remember what is ANOVA, it's analysis of variance. Using ANOVA, we have to follow a strict rule. First, we have to make ANOVA table. Simply table similar like this in order to evaluate this hypothesis. And then we need to test the null hypothesis by measuring the alpha, by deciding the alpha, and then we need to test whether the beta 1 equals to 0 or not. We then need to reject the null hypothesis based on the p-value that we obtain. But here, because the p-value are less than alpha, which is just 0.01, then we may reject the null hypothesis. So how about the confidence interval? The confidence interval for mean value of y for a given value of x is given by this equation, where here the degrees of freedom for t is equal to n minus 2. Maybe you remember that this linear regression has two main main points, which is to see how confident the data are, and the other thing is to predict the unseen line. So here, as we have the confidence interval, we also have the prediction interval, but the prediction interval is quite tricky because it has higher error than this confidence interval, because we have unseen data. So based on the previous example, we need to calculate the confidence interval and also the prediction interval. For example, we have 90% confidence and prediction interval. We have two different values. We see the error for prediction interval is much higher compared to the confidence interval, because this prediction interval we have unseen data. So in order to select which data is correct for our line, it has a lot of variance. So resulting in a more errors. So the variance is higher. Okay, that's probably for linear regression. We then may continue to correlation analysis, because as I mentioned earlier, for the regression, there are correlation between the data. So basically, this correlation analysis is used is a group of statistical techniques used to measure the strength of the relationship between two variables. And here we have also scatter diagram. In a scatter diagram, we can check the correlation. We can analyze the correlation from this scatter diagram. How the effect of this dependent variable compared to independent variable, and we may check whether is it causality or not, because basically correlation cannot be used to prove the causality. Coefficient determination is only shows whether there is a relationship between the independent variable and also the dependent variables. And this correlation coefficient is not a percentage value. So if we have a 0.7 correlation coefficient, that does not mean 70% variation from the variable, from the dependent variable. So here we have the coefficient correlation, and this coefficient correlation is a measure of a strength of the relationship between two variables, and it also requires interval or ratio scaled data. It varies from -1 to 1, and the values of -1 or this 1 values indicate perfect and strong correlation, while where the value close to 0, it indicates the weak correlation. Negative values only indicates an inverse relationship, and positive values indicates a direct relationship between the values. So here we have example correlation. For this correlation, we have positive correlation and negative correlation, and also zero correlation. Here for positive and negative correlation, we have perfect positive, perfect negative, strong positive, strong negative, and also weak at both correlation, positive and negative. We can see by the scattering of the data. If the data fits perfectly on the regression line, we have a strong correlation, but a perfect correlation. If it's small variance, we have a strong correlation, but if we have a high variance here, we can say it's a weak correlation between the data. And here, as I mentioned earlier, this correlation does not necessarily imply causation. There are 4 possibilities if X and Y are correlated. It could be X causes Y causes X and Y are caused by something else, especially for 3-dimension graph, because usually we only deal with 2-dimension graph, which is Cartesian diagrams, but we cannot forget about 3-dimensional three-dimensional diagrams. For example, maybe later you can study about the electrochemical impedance spectroscopy, where the x and y and z axis, but usually we only display the x and y axis, while we did not really concern about the z axis because it has no direct correlation, but it has correlation. And the next one is confounding, where the effect of x and y are hopelessly mixed up with the other variables, not only one variables, it mixed up with lots of variables. So here we have a causation example. For example, here the city with more police per capita have more crime per capita. As ice cream sales go up, shark attacks go up. How can we correlate this causation example? What do you think? It does not necessarily correlate with each other, but if we draw a graph or diagram, we can find this correlate very highly. Okay, so we need to determine the R square for measuring the correlation efficient. This coefficient, we call it coefficient of determination. This coefficient of determination is the proportion of this total variation in the dependent variable y that is explained or accounted by the variation in the independent variable x. And this coefficient of determination is the square of the coefficient of correlation, and it ranges from 0 to 1. If you remember, this coefficient of correlation ranges from -1 to 1. So if we square the values, we can simply shrink the range from -1 to 1 into just from 0 to 1, because it's squared values, where the maximum of squared values of -1 is 1. So we have we shrink the values. Here are the formulas for R values and R square values. So if we go back to the previous example here, we still did not finish the example yet, so we still have the data. Then we can find the coefficient of correlation and the coefficient of determination, which are R and R squared. Here the R squared, the R value is negative 0.9479, which is a strong negative correlation, and the R squared is equal to 0.8985, which is equals to 89.85% of this variability of sales is explained by rainfall. Okay, so I think that this should be enough before your final exam. So as usual, you need to work on this exercise, and you have 1 week as usual. And please don't forget to check at SIAC to check your exam schedule. I know this will be the last week before a final exam, but the final exam is not due until June. It will start, as I remember, it's from June 8th, and probably your schedule for final exam will be June 13th. But I suggest you better check on your schedule. So you have plenty of time to do some exercise before final exam. I will inform you later if there will be if there is a change in the schedule. But for now, the schedule will still for final exam will be on June 13th. Okay, thank you very much for your kind attention. See you on final exam.